My name is Jeff McCullough. I teach AP Statistics at St. Mary's, and if you want to follow my blog, I just started this a couple weeks ago, jmccullough1 at wordpress.com, and my Twitter account is at jmccullough1. Here's a question for you. Where would you rather live? A place where the median high temperature is 72.5 or 73.5? They're probably pretty similar places, you would think. I wonder where the median high temperature is higher, in Memphis or Los Angeles? Do you think it's a lot higher? I wonder. This is from weather.com. This is Memphis, and this is Los Angeles. And you can see that actually the median temperature is very close, but there's a lot more variation in Memphis weather. It goes down to 48. We saw that this winter, highs of 91 for median high temperatures. Whereas in LA, it tends to be, pretty nice all year round, actually. And there's not nearly as much variation there. You see lots of variation here, not as much there. Let's talk about some of these measures of spread and different things we do with data. The first thing you may notice I did with my Memphis data here of temperatures is I organized them by smallest to biggest. And that really helps. Before you want to find anything like median, you definitely want to organize them numerically in ascending order first. Mean, you probably all know how to do. You think of that as the average. You basically add them up. I think these total to be somewhere like around 854. There are 12 months, so you do 854 divided by 12, and you get your average, which is somewhere about 71.2. The median is different, though. It's the number in the middle. And so you just kind of count out 1, 2, 3, 4, 5, 6. Right there is kind of the middle of the data. And you notice there's kind of two data pieces that are right in the middle. And so if that happens, you basically just add those up. You say 71 plus 74. Divide them by 2. That averages them. And you get 72.5, which is the median temperature in Memphis, median high temperature in Memphis. The mode in this case is just the most repeated term. You can see that there are two 62s, so 62 is the mode. The max is the highest temperature, which would be 91. The min is the lowest, which is 48. Incidentally, the difference between those is the range, is when you do the max minus the min. That's the range of the data. So 91 minus 48, that would be the range. Q3 is the quartile 3, is what that stands for. And it's here, the upper half of the data, I guess that would be here, Q3. What's the middle of these 6 pieces of data here? So we cut it in half to 6, and then we cut that in half. That's like the middle of the middle. The median. The word median means middle, like Durham Parkway has a median in the middle of the road. So you have to think in the middle of this piece of data. And so this is where Q3 would be. And of course, we have to do the same thing we did there. We average those two. So Q3, I think, would be 86. And then we take this and we average those two terms. Whatever that is Q1 if we average those. And N is just a number of terms. So N is 12. There are 12 terms here. But I want you to notice something that a lot of stat students don't get right away, but I want you to get it, is Q1, like in the first third of this data here, like this is Q1 right there, but there's exactly 25% of the data pieces. 3 out of 12 data pieces are in Q1 right there. In the second quadrant, or the second part of the data there, there's exactly 25% of the data, 3 of the 12. Again, between these two, 25% of the data. So this median really splits it up. If you think about it, there's 50% of the data is on one side of the median, and 50% of the data is on the other side of the median. So we're really separating this data into equal chunk sizes here. And that's part of what this 5-number summary does for us. So if we look at the 5-number summary, we think of that the min and max, Q1, Q3, and then the median in the middle there for Los Angeles and Memphis. And I went ahead and did a box plot. And so what a box plot is, and we use it quite a bit with stats. So you think 91 is 91 is right there. That's that point right there at the end of the whisker of the box plot. 86 is Q6. That basically is this point right here. 86 is kind of the edge of the box. The middle of the box is this line right here. That's actually the median right there. So that point right there, which is right about 72.5, is that line represents the median, not the mean, the median, the middle of the data. And then 57.5 is this point right here at the edge of the box, and then 48 is the minimum there. And so those 5 numbers, if you know those 5 numbers, you could plot those points and then basically draw your box. And you see how much data is in, say, this right there. What percentage of data of the Los Angeles data? There's exactly 25% of the data is there. Exactly 25% is there. 25% is in this part. 25% is in that part. So it really breaks it up into 4 equal chunks, even though one may be more spread out than another. This is not really part of the lesson, but this data tends to be skewed right here. It looks like it's kind of got more spread to the right than it does to the left, and it's much more compact. The IQR is the interquartile range. It's basically the box here. That's basically your IQR. So if you do, I guess formulaic, it'd be Q3 minus Q1. It's a distance there. IQR is how long that box is. The semi-interquartile range is actually when you divide the IQR divided by 2. And so what's interesting is if you take the IQR for this one and divide it by 2, you basically split it somewhere down here, like it'd be, what is that? Let's see, 81 minus 69.5, and then divide that value by 2. And so it ends up being half of that data, not the same way that the median cuts it in half, but numerically half of the distance there. It's a semi-interquartile range. Which box plot is homogeneous? So this is not a term we use in AP Stat, but when you're doing psychology stuff like y'all are. Homogeneous is when it's more compressed in its appearance. So this one would be more compressed, and heterogeneous is when it's more expanded in its experience. So you can see the data has more spread to it here, has less spread. So this one basically means it has less spread. It's compact. This one is spread out. It has more. It's expanded there. And last thing, the inclusive range is a little different than the regular range we mentioned a minute ago. It's the max minus min, and then we just tack this on. That's the inclusive part. We're adding 1 to that. That's something we do sometimes in stats to account for error. Standard deviation is a pretty complicated formula. It's a measure of spread, how spread out the data. You can see how important that was in the weather example. They have almost the same median, but wow, way different weather because the spread is way different. And so, but this is a measure of spread, how spread out the data is. You take each data piece, subtract this is the mean, that's X bar, which is the mean of the data. You subtract those for each data value, and then you would sum those, square those, and sum them, and then multiply by 1 over n minus 1, and then take the square root, and that is the standard deviation. Pretty complicated formula. I don't think you'll have to figure that out by hand. Usually a calculator or computer does that for us. Normal curve is kind of a big deal. So this is something we use a lot in stats, and we're basically using a standard deviation as a ruler. So you can see that we're going, like the mean of the data is in the middle of the bell curve here. Here's some stuff about that. You may want to write that down. It's kind of interesting. But if you go 1 standard deviation over to the right, if I add 1 standard deviation, this is the term for standard deviations, sigma there. As a Greek letter. And so if we add 1 direction or we subtract in the other direction, that's considered 1 standard deviation out from the mean. And so what happens here is 1 standard deviation out from the mean if it's a normal curve, and a lot of data fits in this kind of normal model. It may not be perfectly normal, but it kind of looks like this shape, this bell curve, unimodal. That means it has, it doesn't have 2 humps. It doesn't look like that. That would be bimodal. 60 68% of the data is somewhat average in there. That's the bulk of the data is going to be within one standard deviation of the mean. It's going to be relatively close. 2 standard deviations away from the mean, 95% of the data. The bulk of almost all of the data, and it really get unusual if you get in more than 2 standard deviations away. 99.7% will be within 3 standard deviations. We use this oftentimes with IQ or many different measures that we do with data. Here's how this is helpful, and we have to get into Z-scores here in just a minute. But let's say Sandy got a 680 on the math section of the SAT. Sandy got a 29 on the math section of the ACT. Well, I think on purpose, the SAT and ACT do not have the same scoring system. Which test did she do better on? Well, these are true means and standard deviations of the ACT and SAT. Typically, they change slightly with each test, but those are pretty typical values. How do we compare? It's still hard to compare which one did she do better on. Which one should she maybe send into the college of her choice? And so we can actually compare these mathematically if we standardize them. And so we standardize with something called Z-scores. And Z-scores, when you take Z is equal to the data piece, the X value, minus the mean, divided by the standard deviation. And that will always give you a Z-score. Z-scores does not have like a unit of measure to it at all. And it just kind of standardizes everything. And so here, if I want a Z-score for this piece of data, this I say Z equals 680 was a score she got, minus 500 was the mean score, over 110, and that's going to be equal to, and then you just solve that and get it. And here we get Z-score of the ACT would be 29 minus the mean of 21 divided by the standard deviation of 5.2. So I went ahead and used my calculator and figured out that this one is 1.6 and this is 1.6 Z-score approximately, and this is 1.5. And so you can see that this is the better score in relative to the mean. We standardized the score. We can compare 2 different scales and figure out which one actually was better. And so we can say for sure this is the one she should turn into her college because it was the better score. Z-scores, that's just a few things about Z-scores if you want to write that down. Does not change the shape. They don't have any units of measure. Those are big important things. Let's say we have a Z-score of negative 1.2 and we want to figure out what score did the student receive on the test. So we have kind of weird information, and we have the mean up here, we have the standard deviation, and we have the Z-score. Well, if you have all 3 of those mathematically, you've got enough to solve, because you basically say, well, Z equals X minus the mean over standard deviation, right? So Z is negative 1.2. And X, well, we don't know X, but we know the mean is at 1045.7, and the standard deviation is 221.9. So then it's just a matter of solving this algebraic equation, and most of you can probably solve that. You're basically going to multiply by 221, multiply by that on both sides. And it cancels over here, and then you basically have to add the 1045, so we're going to add that over here, 1045.7, and that goes away over here when you add 1045.7 over here. And you have your X value of whatever that is, and I think it's one of those. Type it in your calculator, and you get the answer there. Finally, converting to T-scores is a very easy conversion. You just do T equals 10Z plus 50 to convert. And the reason we do this, big thing is we have all positive values. We never have negative values now. And so we can convert this just by saying 10 times that, 10 times negative 1.2 plus 50. And we have our T-score there. I thought you would like this graphic. I'm running out of time here, but here is another one.